And thank you for both the organizers for this nice workshop and for all the organizers for this very nice event. And my talk today is based on a joint work with Axel and Verfürth and my supervisor Barbara. And in this talk, I will present an offline-online preconditioning framework for diffusion problems having randomly perturbable multiscale coefficients. First, introduction, and let me introduce our problem right away and then explain what motivates us this study. The image you see here, this is an example for the type of multiscale coefficients we are interested in. And this type of coefficients come from or influenced from composite materials, where this material has a periodic microstructure. And during the fabrication process of these structures or materials, then due to production mistakes or so on, there could be a small number of perturbed microcells. And these perturbed microcells then results in random difference in the material. So in this image, these places where this small yellow square has disappeared are the places where there's a defect in this cell. Now, what we want is to solve the diffusion problem or the derivation from the diffusion problem with this coefficient for Dirichlet boundary conditions. But this is not all we want. We want to solve this problem in an independent setting for many realizations of this coefficient. Now, let me also introduce the mathematical form or the nice form of this coefficient. This model is initially from Claude-Lewis, and it's very helpful for our setup. So here this A epsilon acts as a background coefficient, and in this case, this is now the epsilon length squares in this dark purple color, and on top there's a small second this yellow square. And then we have periodically arranged them over the whole domain. Next, this V epsilon, this acts as a defect coefficient, which acts or switches on or off depending on this BP here. So this BP is kind of a switch that activates or deactivates this defect. And then, this BP also, it includes the characteristic function of the defect and also obeys IID Bernoulli law. So here we consider the Bernoulli distribution, but it's also possible to consider other distributions, but this is what it makes sense here. And then for a given defect probability, then this decides if there's going to be a defect on each of these smallest squares. Now, this is the idea of this coefficient. And let me then introduce some terms here. We consider our reference continuous or exact solution in the full Hilbert space, and for simplicity, we take the unit square as our domain, and f is square integrable. So we use two discretizations to solve this problem numerically. First is the fine scale finite element space, which resolves for these fine scale features in our multiscale coefficient, and then a nested coarser space. We will discuss this a bit later in a little bit more detail. And now this is my problem setup. Now, we know that many multiscale problems, including this one here, are difficult to solve numerically for one reason: the coefficient is ugly. They are obviously of multiple scales and heterogeneous and often high contrast. So the discrete system, this is often ill-conditioned. And then in the setups like Monte Carlo simulations, which is exactly what we want here, then there's the second reason that we have to solve this ugly system for many samples or many realizations. And this is highly expensive. And on the other hand, if we want to solve this problem using an iterative solver, particularly the conjugate gradient method, then the convergence of the solver is really slow due to this ill-conditioned system. So one remedy to fix is the preconditioner, which we saw in many interesting talks this week. But to remind the essence of it, just in a short sentence, for those who are probably not familiar with preconditioners, we can think of a preconditioner as a briefly applicable operator that acts as an approximate to the inverse of a stiffness matrix. And once applied this inside an iteration, then it improves the conditioning and then drastically reduces the number of iterations we need for a convergence. And this is the idea. So there are nice preconditioners, and one of them is the two-level additive Schwarz preconditioner, which also we saw in a very nice talks and in detailed explanation. Now, the question is, this additive Schwarz is a robust precondition that we can use for a problem like this. But the question is, the catch is, additive Schwarz acts on the fine scale patches, and we want to solve this for many samples. That means we have to solve these fine scale computations for hundreds or thousands of times, and this is really expensive. So the question then, how can we keep this additive Schwarz robust but make it cheap across many samples? Now this is the motivation behind our talk today, or like this study. And we propose an offline-online construction for fast and robust approximation for the realization-dependent exact additive Schwarz, two-level additive Schwarz precondition. Now, this is the rest of my talk today. I will explain a little bit about domain decomposition and our two-level additive Schwarz preconditioner framework. We already saw this, but it is also our baseline, so maybe let's recap just in a couple of slides. And then our offline-online framework, error analysis, and some numerical experiments. First part here. We work in the classical additive Schwarz framework, as I said, and here we consider a coarser space or coarser mesh. And on this coarser mesh, we also consider another fine scale mesh, which is a refinement of this coarse mesh. Then we want to decompose this fine scale space into a global coarse space plus the overlapping of fine scale subspaces. These subspaces correspond to a coarse vertex in our domain. And then for a given coarse vertex, we then define our subdomains or the patches like as the support of the corresponding basis function of this vertex. And this is what we have. So these patches you see here are such constructed patches. And these patches do overlap, but this overlap is uniformly bounded. Not these two, sorry. But yes. And then all these patches in our domain, they are similar in structure. Now, this is our geometric backbone. We have some nice patches and subspaces. Now we want to find a good local operator that would extract the best correction on each of these patches. And this is what exactly the local Rix projections do. So we define our local Rix projections here, Pi in this variational form, and then this Piz is the best approximation to a function C in the energy norm in this subspace Vi. And this solves the Dirichlet problem on this patch and captures the fine scale corrections on each patch. We also then introduce or define our stiffness operator L from fine space to its dual by this variation. And so I want to stress here, this is not just the inner product, but this is the pairing between the duality pairing. And then we define the local solution operators, VIs, in this way. So we have the composition of VIs and L gives us this local X projection. When we have this, we can then finally write the two-level additive Schwarz preconditioner in this form, where this V naught is the correction on the global coarse space. So this is in this same structure here, but here this W is now in the global coarse space, VH, capital H. And then we have the all the subspaces here, and together we get the two-level additive Schwarz. And this is the corresponding preconditioned operator. Now, if we solve our problem using this two-level additive Schwarz, as I said, is robust, but to show, if we now need to solve this problem for many samples, for example, n number of samples, then the total minimum cost would vary at like n times the sum of number of patches per sample times the cost per patch and the number of iterations per convergence and the cost per iteration. So this is much smaller for robust solvers. However, these terms are big, and since that, we end up still with a huge cost. So this is why, even though we have robust preconditioners, it's not practical or good enough in the case of multi-sample settings. Now, keeping this motivation in mind, we can introduce our offline-online framework. This offline-online framework is mainly possible due to its structure. For two main observations here. First is the localized structure. Now here, due to our periodicity and also the localized structure of our defects, then these local solution operators, VIs, they depend only on the coefficient that is localized into this patch. And any other defect that's outside this patch has no influence on this operator. That is the one thing, and the second thing, the repetitive nature. So all the patches have this similar nature, similar structure. So if we consider a single reference patch here, this red one, then all other patches are minimal variations of this red one, varying only at positions of a defect. Now, for example, if we consider this blue and red one, this is just the same exact patch up to translation. Now, this is what makes it, what influences our offline-online strategy. And now, if there is a way that we can extract the right information for each of these defect locations here, then this is what we actually need to construct any BI that corresponds to any other patch. I mean, we need to do it in the correct way, extract information, and that is what we do in our offline-online stages. So in the offline stage, we now consider a reference patch, and then we want to construct a basis of reference coefficients considering single defect configurations. So in this one, this is now the first four configurations. This is the case where we have no defect on the patch and defect in the first place, second place, third place, up until it covers all places. So in this particular case, we would only have 17 such reference coefficients. Now, once we have these reference coefficients, we then want to compute these local solvers for each of these reference coefficients. And this one, what we compute here, we now going to pre-compute and save it. This is all we are going to use for any given realization of it. And just note that we only did 17 patch fine scale computations. And now we would go to the, Did I miss something? Yes. Now we go to the online stage, and in online stage we now have a real coefficient. In this real means like a realization which have many defects, and we localize it into a given patch, because that's how we did patch solvers. And on this patch, for example, if we consider this patch here, what we did in additive Schwarz, we computed our local solver exactly on this given exact patch. But what we do here, we would now find an approximate solution, local solution on this patch using our pre-computed and stored these local reference solutions and some mu values, that in a way that the sum of all these mu values should add up to 1, and all mu's that are greater than or equal to 1 should be either 0 or 1. And mu naught is 1 minus ndef. Ndef is now the number of defects in a patch. In this case, we have 2 defects. So these 2 defects can come from this coefficient and this one. So in these 2 places, the mu is activated and 1. And then this is the mu naught where there's no defect. This is now because 2 defects, mu is minus 1 here. And then if you notice, all the places that are actually activated are 2, 3 and 0. Everything else, the mu values are 0, so we don't have any activated local solutions. Why? Okay. And this is the idea, and now finally we can introduce or show our offline-online preconditioner, and this preserves the exact or like 2-level additive Schwarz preconditioner. And here, this denote, this is the coarse-scale correction. This is computed exactly as this, but like in our study, we also came up with offline-online strategy to compute this even more efficiently. But I wouldn't go into detail. I mean, efficiently, but exactly still. This is cheap still because this is done on the coarse scale. Now, this is the idea. But now the remaining question is, does this approximation destroy the PCG convergence? And that is what we would discuss in our error analysis. And we answer this question by comparing it with the exact operator, exact or like 2-level additive Schwarz precondition operator. And now remind that P is our preconditioner and P is the preconditioner that is seen by the preconditioned conjugate gradient method. So the additive or like classical additive Schwarz theory tells us that the spectrum of P or like P, the additive Schwarz precondition operator P, has a spectrum that is uniformly bounded or like yes, and then that means exactly this, there exists C1 and C2 positive constant where this statement holds. And that means all the eigenvalues of this operator now lie in this C1, C2 interval. And that means we have the precondition, or sorry, the condition number bounded by this ration. So this is the key reason that these PCG solvers are robust. And in this is from again the classical theories. I wouldn't go into details because we actually saw these 2 results many times. And then because of this bound, or like upper bound, then we have these nice error estimates. Now our goal is to show that similar bounds hold for our approximated P. And how we would expect to do that? By showing that P tilde is just a small perturbation of the exact P. To do that, we would first define the perturbation constant as the worst case relative error between the two operators. Now, once we have this, because we know that the additive Schwarz two-level additive Schwarz has this bound C1 and C2, we can actually easily show that our approximate operator P tilde is bounded by these bounds. So we have the lower C1 minus eta bound and here C2 plus eta upper bound. Now, if eta is small, that means the perturbation or the difference between operators, they are small, particularly less than C1, then we have here positive bound, positive lower bound, and that guarantees the stability of our approximated preconditioned operator. That means we would have all the spectrum of our preconditioned operator, all the eigenvalues, now lie in a shifted interval of the exact precondition. That is the C1 minus eta and C2 plus eta. Once we have this thing, we now can directly use these results from classical theories, and we have these error estimates where this condition number is now bounded by this proportion. So this is the idea, and it guarantees we also have PCG convergence, a robust convergence, as long as this perturbation stays small. Now let us see some numerical experiments. I realized maybe I'm a bit too fast. I have so much time remaining. So some numerical experiments, and here we used the sin pi x, sin pi y right hand side, and then we have considered the average PCG iterations against varying defect probabilities, and also so we compared our method with two reference methods. First one is the obvious additive two-level additive Schwarz method. The other one is that because we are in this rare defect scenario, in a sense, it also made sense to compare it with a constant preconditioner that is constructed on the zero defect coefficient. And this orange is the this constant coefficient preconditioner, and then this B tilde, not B tilde, here it should be B, and offline online B tilde, and then blue is the additive Schwarz solver or additive direct solver, and then this green is our offline online preconditions solver. And we also, these three things corresponded to three different contrasts, and here the contrast between the variables, the alpha beta, is 10, 100, 500. And we see here our offline online and the additive Schwarz methods both almost overlap, and then this constant preconditioner, this increases the iteration number drastically. So here I don't want to say our method is always good, because for example for much smaller constructs it makes sense to do this because the setup cost is much smaller, so it makes sense to use a constant preconditioner, and the number of iterations is a bit higher, but that is fine considering the setup cost. But as it increases, the contrast increases. For example, in this case, the difference between the iterations is about, I think, 120 something. And this is for one sample. And if we want to solve this for like 100 or 1,000 samples, this is huge. Even though the setup cost here is smaller, the iteration cost gets much higher. And then, so this is one of the main gains in our method. And yes, so this is about this. And then We also, PCG convergence. Again, we see the same type of behavior we would expect. We have the offline online and the additive Schwarz, they almost overlap. And then the constant preconditioner, the convergence rates are much slower. Now, this is our method. So we proposed, because I have time, I can recap everything. We proposed an offline-online decomposition preconditioner for diffusion problems, having these localized defect structures, and then it avoids fine-scale solver solutions for all the samples, and only use few fine-scale solves. And we did some perturbation-based analysis, and finally our numerical experiments confirm that it's actually a promising solver in this type of scenarios. So this is it, and thank you very much.